Today we are going to look at 8.6, solving exponential equations. First, we're going to start off easy. If I've got 4 raised to the x plus 5 power is equal to 4 raised to the 2x minus 2 power, in order for these two quantities to be equal, if they have the same bases, that means their exponents must be equal. So I set x plus 5 equal to 2x minus 2. Solve for x, so I move the x over, move the 2 over, and we get x is equal to 7. Next, if we've got 36 raised to the x minus 9 is equal to 6 raised to the 2x, my bases aren't the same. But we do know that we can rewrite 36 as 6 squared, and that's being raised to the x minus 9. If I have a power to a power, I'm going to multiply, so that becomes 6 raised to the 2x minus 18 equals 6 raised to the 2x. Now, in order for these two pieces to be the same, I have to be raising the 6's to the same power. So I set 2x minus 18 equal to 2x. When I move the 2x over, the x's cancel, and I've got negative 18 equals 0. That's not true, so there's no solution. And number 3, we've got 25 raised to the x minus 1 is equal to 125 raised to the 4x power. 25, 125 aren't the same, but 25 can be rewritten as 5 squared, and 125 can be rewritten as 5 cubed. We know power to a power we multiply, so we've got 5 raised to the 2x minus 2 equals 5 raised to the 12x. Again, in order for these two pieces to be equal, these exponents must be equal. 5 to the third is not the same as 5 to the fourth. So I need those two pieces to be equal, so I set 2x minus 2 equal to 12x. Move the 2x over, and we've got negative 2 equals 10x. Divide by 10, and we get x equals a negative 1/5. Alright, so just remember, if two powers with the same base are equal, then their exponents must be equal. Reviewing some of our logarithmic rules, I know that if I've got 5 with a base of log with a base of 5 times 5 to the 6th power, that log base 5 of 5 cancels, and that just equals 6. Log base 3 of 27 raised to the x power, I can rewrite 27 as 3 cubed, so that becomes 3 raised to the 3x power. The log base 3 of 3 cancels, and you're left with 3x. Alright, for number 3, we've got log of 1,000. Hopefully you remember that if there's no base there, it's the common log with a base of 10. And then I take 1,000, I can rewrite 1,000 as 10 to the 3rd power. So I've got log base of 10 cubed, that cancels, and that leaves you with just 3. Alright, we're going to use these rules to help us solve for different kinds of exponential equations. This time we're not always going to have that base be the same like we did in the first few problems. So if I've got 2 raised to the x power is equal to 31, I can't rewrite 31 to have a base of 2, but I still need to get to that exponent of x. So what I want to do is I want to get that 2 to cancel out. This is where I'm going to use the rules, a simplification of that we just reviewed. So the only way to get rid of that 2 and to get x by itself is if I was taking log base 2. So if I took log base 2 of 2 to the x power, that would cancel and I'd be left with just x on the left. But we know anything we do to one side, we have to do to the other side. So on the other side, I'm also going to take log base 2 of 31. So x is equal to log base 2 of 31. Now we're not going to leave that as our answer. We reviewed the other day about how this can't go in our calculator just like that, but I'm going to use the log of base formula. So to evaluate this in our calculator, we use log of 31 over log of 2. And we get that x is going to be about 4.954. For number 2, we've got e raised to the 2x is equal to 6. Again, I can't rewrite 6 to be a base of e. So I want to get that e to cancel out. And I know the way the e cancels out is by taking the natural log. The natural log of e to the 2x, the natural log of an e, and the natural log and e cancel, which leaves me with 2x on the left-hand side. So since I took the natural log on the left side, I take the natural log on the right side. So we've got 2x is equal to the natural log of 6. To get x by itself, we divide by 2. X is equal to the natural log of 6 divided by 2. We enter that into our calculator, and just be careful that you do the natural log of 6, close out your parentheses, and then divide by 2 to get x is about 0.896. Number 3, now I want to get to the x, I want to get to that exponent. What I want to do is make sure that that piece is isolated before I start taking the logs of each side. So I move the 5 over, and I get 3 to the 2x is equal to 7. Now I want to get to that exponent, which means I want to get rid of that base of 3. So I take log base of 3 to the 2x power. That cancels, leaving me with a 2x, which means I have to do that to the other side as well. So log base 3 of 7. This is where things are going to get a little tricky. We would divide by 2. And it looks easy enough here, but entering this into our calculator is going to get a little more difficult. Because we know to put this in our calculator, we have to have the log of 7 divided by the log of 3. But we're taking that entire piece and dividing it by 2. So when we put this in our calculator, we have parentheses. Log of 7, close out the 7, divided by log of 3. You got to close out the 3, and then you have to close out the numerator. Because remember, we want this entire thing divided by 2. And we get that x is about 0.886. Turn your sheet over. Okay, so solving logistic growth problems is similar, just with a couple extra steps. If we have a fraction on one side and a number on the other side, I can make that 10 into a fraction by putting 10 over 1. And then I've got two ratios that equal to each other, so I've got proportion. In order to solve this, I'm going to cross multiply. So I've got 12 times 1, which just gives me 12. And then I cross multiply 10 times the whole quantity, 1 plus 3e to the negative 2x. Now you can distribute that 10 in and get 10 plus 30e, but I think that's just adding an extra step. So right here I'm going to divide by 10, and 12 divided by 10 is 1.2. You can keep it as a fraction, or you can write 1.2. It doesn't matter as long as it's an exact answer. So if like this one was 1/3, you wouldn't write it as a decimal because that would be 1.3 repeating, and you wouldn't be able to hold the true value. So since 12 divided by 10 is exactly 1.2, you have the option of the decimal or the fraction. So that equals 1 plus 3 times e to the negative 2x. Remember, my goal is to get to that x up there. So we do solving like we would solve any other problem. We subtract 1. 1.2 minus 1 is 0.2 equals 3e to the negative 2x. We divide by 3. And 0.2 divided by 3, now we come into that problem. When you divide that, you don't get an exact decimal like 0.2. So this as a fraction becomes 1/15 equals e to the negative 2x. If you're wondering where that came from, if you take 0.2 divided by 3, not an exact decimal. I can't write that like the 0.2. So I want to leave that as a fraction, so I do math 1, frac enter, and I get 1/15. So now I've got my piece isolated that has the exponential variable. Now I want to get rid of e. To get rid of e, I take the natural log. The natural log of e cancels, leaving me with a negative 2x. So since I took the natural log of that side, I have to take the natural log of this side. When you're solving, you don't have to worry about expanding, condensing, just use what you have. So I've got the natural log of 1/15. And to get x by itself, we divide by a negative 2. So in your calculator, we take the natural log of 1/15. The 1/15 is all in parentheses, and then we divide that by a negative 2 to get that x is about 1.354. Alright, we are almost done. We have one last problem, and that is our real-world application problems. Okay, so the Department of Natural Resources puts 200 largemouth bass into a new lake. They expect them to grow at a rate of 15% each year. So hopefully the very, very beginning of our chapter, which I know is a really long time ago, is coming to play, and since we're growing, we're going to use our exponential growth factor, or exponential growth equation. So that's y equals a times 1 plus r raised to the t power, where a is your initial amount, and our initial amount is 200. 1 plus your rate as a decimal, so 15% is 0.15 as a decimal, and this is per year. Make sure that you combine that together. So our equation is y equals 200 times 1.15 raised to the t power. How many bass are there in 10 years? So we're given one value. Our equation has two variables. We've got y and t. We replace the variable that represents time, which is your t. So we've got y equals 200 times 1.15 raised to the 10th power. Now remember, on the last quiz we had some people that got this wrong. You don't multiply the 200 times the 1.15. Order of operations says you have to evaluate exponents first. And really you don't even have to worry about that, because if you just type the whole thing into your calculator, it does the work for you. So 200 times, or parentheses, 1.15 raised to the 10th power. So that gives you about 809 bass. And remember, you're just going to round to the nearest integer. Integer being non-decimal answer. And our last problem, when will there be 420 bass? Round to the nearest hundredth. So we go back to our original equation, y equals the 200 times 1.15 raised to the t power. So again, we have two variables. We've got y and we've got t. 420 bass is representing your y variable. Now, up until this point, the only way we knew how to solve this kind of problem was in our calculator, but now you can solve it algebraically, and you're going to be expected to solve algebraically on your quiz. So 420 divided by 200 reduces down to 2.1. Now this is really where you have to kind of embody the idea of what it means to solve an exponential problem. I want to get to the t. I have to undo that base of 1.15. So to undo it, I've got log of 1.15. That's how that cancels to give us t. So that's what they do on the other side as well. Now this, remember, you have to use the change of base. You can't just plug that into your calculator. So you've got log of 2.1 divided by log of 1.15, and you get about 5.31 years. And that's it.